So hello everyone, my name is Mohammed and today I'll be introducing the topic of neural radiance fields. So as I go through this presentation, I want you to keep in mind two important questions. The first one is, can we generate continuous novel views of a scene given a sparse set of 2D images? And the second one is, can we capture geometric complexities represented in a 3D scene from these 2D images? So the first question pertains to a specific problem explored in computer vision known as view synthesis. And what it is basically asking, given some images of a scene, can we generate new images of that scene at a different viewpoint? And then can we do it in a way that's continuous and realistic and consistent representation of the scene? So here you can see an example output of a neural radiance field. The second point that neural radiance fields addresses is 3D scene representation. What can we tell about the geometry of a scene, and can we infer information like depth and the effects of occlusion? If we can synthesize images from continuous new views at a high resolution, then there are significant implications on 3D representations. So neural radiance fields is part of a family of approaches known as volumetric neural renderings. And what is volume rendering? So volume rendering is, simply put it, is a way to take a 3D scene and project it onto a 2D plane at a specific viewpoint, such as a screen. So the goal of volume rendering is to create a 2D images that represents a 3D data set, and that data set could be things like point clouds and voxel data. And one technique to perform volume rendering is known as ray marching, which is used in computer graphics. And what it is basically, given a specific viewpoint of a 3D scene, what we do is we project rays onto the scene, and we sample along those rays accumulated color, transmittance, and volume density. And then the value of the pixel of the 2D projection is a function of the integral of those three parameters. So how do you perform ray marching on a 3D scene with unknown volumetric information, like in the real world? Well, that's where neural network framework comes in. So we can combine a neural network framework to map the inputs and outputs of the ray marching process and train the model with a couple of images in order to make this type of mapping. And in essence, that is what a neural radiance field is. And what makes neural radiance fields unique is that it's an implicit 3D representation. So instead of explicitly having a 3D representation, such as voxel or point cloud, neural radiance fields implicitly model the weights within the weights of a neural network. And what it does is it maps 3D position and viewing angle to a emittance radiance and volume density along a projected ray, and then we can perform ray marching. So the NERF rendering and training pipeline is such. What we do is we query the network along the lines of array to produce a pixel value, and we perform a volume rendering based on the values that of the ray, and then we train it based on the actual training images, and we generate a loss function as such. So there are many properties of neural radiance fields. It's able to achieve state-of-the-art photorealistic renderings. It's able to capture complex scene geometries and can be used to simulate occlusions and mixed reality applications and depth maps. And one really cool thing is that since the 3D information is stored within the weights of the neural network, a 3D model can be reconstructed, which means that a 3D file can be stored within a file smaller than the size of a single image. And of course, with any model, there's some challenges. It requires constrained static scenes, so it's not very good for moving objects. And it requires many images with consistent spacing, at least 80 well-spaced images. So that's neural radiance fields within 5 minutes. Here are my references, and thank you very much for listening.